Okay, we don't have a lot to cover today, but that won't keep me from filling up the hour. I sent an email out. You know that the scores are uploaded. What I want to do is spend a few minutes explaining how you can check to make sure that things were graded correctly, what you can do about something you didn't like. So let's, I guess, initially go to this, which is bugger. Okay, so exams, here we go. This is the link. So you can find your exam here, not mean the form you had, you can find the key here, so you can figure out what I thought the right answers were. And then you can look at Blackboard, and so there's this column, well, I see it as a column, EX1, whatever, that has your score. But if you look in the comment field, you will see something that looks like this. And it'll tell you what version you thought you had, which was one of the bubbles you put in on the exam. And then for the rest of it, you'll see these things in brackets or in braces, right? And that will tell you, it said 1 through 4 were, in this case, were graded as a unit. And all I need to do is find the old exam here. I don't know how I can lose that exam in this little space. Says they're graded as a unit. For 1, you put down A, 2, you put down B, 3, you put down A, 4, you put down B. You got 5 points for that in this, for this individual anyway. And you go to the next one and so on, right? If you see an X behind one of the question numbers, it means you put down 2 answers for that question, which means you got no credit for it. And this is, by the way, is what I'm referring to. 1 through 4 are graded as a cluster. The key will tell you how many points you got for no mistakes in that cluster, 1, 2, and 3, etc. And that's true all the way through the exam. So you can find the exam form you took online, you can find the key, you can find what the machine read on your problem set, on your Scantron. And so you can do the comparison to figure out, okay, I got this one wrong, you know, and you may, I don't know if you can remember what you put down, but there may be some cases where you think, okay, I didn't erase something, I actually picked up, I think I corrected all the eraser mistakes. But if there's a blank there, and you think, I didn't leave that one blank, we can look at it. But for the most part, the system grading this doesn't make a lot of mistakes. In the past, with the old system, it made lots of them. Those are pretty much going away. So what you're really going to be focusing on here, perhaps, is the possibility of challenging a question. When you look at, you know, you got something wrong, you go back and look at the key. Maybe you disagree with the grading of it. You know, maybe you'll decide, okay, well, the key said there were no no data in this problem, but I think data are, you know, indicated here. There is a particular format you can follow to send in a challenge. It's given in the syllabus, and basically you write down what the problem was, what your answer was, what answer the key said, why you think your answer should be right. And you're allowed to challenge 2 questions as an individual. And when I say 2 questions, I mean 2 clusters, right? This, if you didn't like the grading of 10 through 13, we'd call that 1 question. And I would say about every exam, there are 1 or 2 cases where I screwed something up. It's possible, if I see something, think, oh, I got that, I put the wrong answer down on the key. First of all, at this point, I don't undo the grading, right? If I decide I used the wrong answer on the key, I'm not going to go back and penalize anyone. No one's score will go down. But I may regrade for the whole class. So it's possible that some of you who don't challenge anything will have a score that goes up if someone else successfully challenges a question that I think was bad.
Yeah, for the cluster, like what if it's only one of the questions that...
Yeah, that's fine. I mean, you can sort of challenge anything about it and say, I think number 11 should have included, this should have been the right answer. But that counts as one, this would be one challenge, whether it's you challenge all of them or just one of them within that cluster. Is that kind of clear? So if you have questions about it, you can come down and ask later. You have 1 week to do this, right? So as of next Friday night, I'm going to say, okay, that's all the challenges or corrections I'm going to accept. Yes? Yes, the syllabus says if you submit something that indicates you're totally clueless, I might take points off. I haven't actually done that before, but there are times when I think this person's head is so far up a dark spot that, they didn't even bother to reread the question. It's reserved for that sort of thing. It's not reserved for someone who, seriously says, look, I think this should have been graded this way. Yeah, as I say, in 10 years, I've never taken points off that I can remember, but I've been tempted once or twice. But it's mostly to keep people from just throwing crap at me and making me work for nothing. Cool? Okay. So we're going to start a new section today. It's on data. All right, we partition the scientific method into models, data, evaluation, revision, and the course is pretty much going to focus on the first 3 of those. So exam 2 will be on data. So data are, we've said this before, they all mean the same thing: observations, evidence. But they're important because they are our tie to reality, to what we're asking about nature. Data represent nature for us. And there's a perspective for the class that I'd like you to adopt, although it's not something that I can easily ask on exams. But there are 3 questions to ask of any claim, right? And this is across the board. If you hear something that sounds weird, the first thing to ask is, what's the evidence? Which is saying, what are the data that led you there? The second question, which is our focus in this part of the course, is how were the data obtained? And third, which will be the last part of the course, is who obtained it. So suppose, to motivate this, suppose I told you that I had evidence that STD, I'm making this up, okay? So just, and it might even piss you off even more that I'm making it up than if it was real. But suppose I told you that I have some data that shows that STD rates in UT students are 5 times higher than they are at Texas Tech or A&M or something. Make it up, I don't care what, okay? And you don't want to believe it, which, I mean, I made it up, so there's a good reason to not believe it. But what types of problems do you think there could be with such data, right? So I made something up so that you'd be motivated to think about what could be wrong if, suppose the data really do exist. What could be wrong with them? Why could it be kind of a misleading comparison? So what would you want to, what types of things would you immediately think of as a way that that might not be real? Population? But what about it? Okay, so in that case, you'd be interpreting the data as saying there are more total cases rather than, that's fair enough, yeah, but we're only about twice their size.
Maybe the sample that you took was like a certain group of people that had them, and then you didn't really take it.
Okay, so the sample might not represent all of UT students. That's a particular type of error we'll talk about in a few minutes called bias. Other question, other ways you might challenge it. So, yep.
Was the test like an accurate test?
Oh, that's a good one. I hadn't thought of that. So yes, are the results meaningful? There are problems with a lot of these types of tests, and so if the tests were bad, that wouldn't be useful as well. Yep. Okay, that's also getting at the bias issue. Another thing that you should ask immediately is how many individuals you're talking about here, right? Student body is big, but if, let's say, I did a sample of 5 individuals or so, you'd think that, well, that wouldn't be very representative of things. So there are lots of questions that we need to start asking about data, and we're more motivated to do that when we don't like what they're telling us. This isn't, this is actually a national issue. The main things I have headlines of are forensic cases, but over the last 5 or 10 years, there's been a much increased realization that the way we've done lineups is seriously flawed. So eyewitness identification, and you know, if we go back to the first day survey, you're aware of that, but somehow people still get convicted with it. So this was an article in the New York Times a couple of years ago on how at least some police units are now trying to clean up the way they administer lineups to avoid problems in those data. This was a few years ago as well. So the breathalyzers that were being used in DC were not calibrated correctly, and it meant that some people were recorded as having higher blood alcohol concentrations than they actually had. And that led to a big uproar. Again, this is bad data. And then something very close to home and much worse had to do with this case in which this person was, there was a fire in a trailer at some town south of here just several years ago. Todd Willingham, I think was his name. And his wife and kid were killed. Some local police went in and decided there was evidence of arson. They testified as much. He was convicted, sentenced to death, and he was actually executed. And people have since gone back and looked at the evidence and said, no, this was not evidence of arson at all. It's actually, there was a commission convened by, I think by the governor on this a few years ago to look into it, because our current governor had actually signed the death warrant in this case and allowed the execution to go through, commission was going to say this was, this was injustice, right? That there was no evidence of this. This person should not have been convicted, should not, based on the evidence, should not have been executed. And the governor at the last minute disbanded the committee, and there was a big uproar about this. So when you get your data wrong, it can have big impact. Oh, course? I had a few problem makers last hour too, who were questioning my handwriting. So, a big part of what we're going to talk about has to do with the following point. It'll be obvious. I'm writing it down mostly to kill time. Data are a special type of model. We know that all models are false. When we talk about data, that means something special. So I'll write this down. So with data, that W slash is with. It means that data often differ from what we think they represent. And we say that data are measured with error. Now, these may not be serious, but we need to be aware of them to understand what the limitations of the data are or might be. So we'll talk about 4 types of errors in data. And usually I go through them in a different order, but we don't actually have time today to do everything I wanted, so I'm changing the order. Rounding precision and accuracy. There's human and technical. Bias. And right now we're going to focus on unintentional. And sampling. So today and Monday, we're going to talk about these 4 types of errors, how to characterize them, how to tell them apart, and how to get around them. And it actually pretty much follows the book in this case. So I'll motivate the first part with a very simple illustration. This could be a scale I get on, or this could be any kind of what we call quantitative measurement. Oops. So this device simply measures distances conveniently. And so we see that this is a dime here. See, it's 17.86 millimeters across the diameter. Would we say that's an exact measurement? Why not? only goes to 2 digits, right? So in theory, aside from the limitations of physics, you know, the fact that atoms are moving and temperatures changing things, any kind of measurement, whether it's linear, whether it's speed, whether it's mass, things we call quantitative measurement. Why am I doing this here? Should have an infinity of decimal places, right? So we'd have some significant digits out front, and then we'd go into decimal places, and we get, so what do we have here? 1787, 86. So in this case, we know that this, you know, should go out many more decimal places until we run into the limits of what, you know, physics is producing in that. So this measurement has to be some kind of an approximation, truncated somehow. Maybe the equipment isn't capable of doing any better, or maybe, you know, maybe the equipment is actually showing us that it's 5732 or something like that, but it's only displaying things, in which case it would be only displaying things to 2, which case it would be rounding them. We know this measure is not exact. That's the main point, and there's nothing we can do about it with this particular instrument. So we just have to accept that this is an approximation. It's measured with some type of error. And that will be true of anything, any measurement like this. And the whole history of physics actually is, at least in experimental physics, is one of getting better and better equipment to make more and more accurate measurements. So this is a simple point, and realistically, I don't think you need to put it in your notes, but you can. So our Rpa error is simply that we cannot exactly measure what we would call continuous values, which would be distances, rates, mass, or weight. Our equipment will always set a limit on how many decimals we acquire or how many we acquire accurately anyway. There's nothing we can really do about this type of error except get better equipment. Okay, end of that one, easy. Actually not going to be very useful to us. For the next one, so I want you to think of a random odd number in the range of 1 to 10. Okay, so concentrate for a minute, let your brain crank through it, come up with a number, and then I want you to plug it into this polling system. And we need you to participate in this case because there aren't a whole lot of people in class today. So we want lots of participants to be able to get a large enough sample to say something. Come on, more you contribute. I think we got to 80 last hour. What should this look like if we're good, if we really are random? What? But in terms of the lengths of the bars, they should be roughly equal except for sampling error. Think it will be? So, number 7, then number 3. Let's see what other people have done in previous years. By the way, what are we illustrating here? What type of error? Someone said sampling. Could be sampling, but it's actually going to be bias. So in previous years, out of 1,000, let's see, how many do I have on here? Almost 2,000. For 1, it's about 0.07, 0.24 for 3, 0.135 for 5, which is interesting, right? You might think that's in the middle. This is about 0.4, and I think this is 0.16. They may not add up. I'm not going to ask you to regurgitate these numbers, but 7 is the highest, 3 is the next highest, and you may or may not remember what you just did, but, right? So there you are. You're just as exciting as previous classes have been. So this illustrates, so you can put in your notes, this was random odd number, 1 to 10, and 7's the most preferred. This is an example of unintentional bias. We can think of this as an unconscious process in which our brains do a couple of different things. One is they're non-random, behave, and we're also not being objective in many cases. And this point won't become obvious until next time, but I want to get it in the notes now. Bias is a consistent, or you can think of it as directional, difference between the data and what they should represent. And that's going to distinguish it from the next type of error we talk about, which will be Monday, because that's as far as I got last hour.